Hello, welcome to Unit 10, Acids and Bases, Lecture A. We're just going to talk about basic properties of acids and bases. Before we get started with talking about acids and bases, though, we need to review a few terms and make sure you have the information straight. Hydrogen, the smallest element, symbol H, made of one proton, one electron, and no neutrons. When hydrogen becomes a hydrogen ion implies that it's the positive ion of hydrogen. That means he is now made of just one proton. He loses his one electron in order to pick up that positive charge. If we have a hydride ion, that's the negative ion of hydrogen minus one, and he now has two electrons instead of just one. Notice what's really important here, and this is going to be important for our acid-base unit. When you have a hydrogen ion, the positive one, he is only a proton. That's all that a hydrogen ion is. It's another word for a proton. You have to be careful. We are going to have these things called hydronium ions. That is when we have a polyatomic ion of 3 hydrogens and 1 oxygen that has an overall charge of minus or plus 1. Hydronium ion is the same thing as saying a hydrogen ion that is aqueous. There's also the hydroxide ion, which is our OH minus 1 ion. You should be familiar with that by now. Notice how similar all of the names are. You really have to pay attention to detail. All right, when we are talking about solutions, acids and bases are all going to be solutions. They're all aqueous solutions, so their solvent is water. We've talked about electrolytes. Those are things that conduct electricity. In order to conduct electricity, you have to have areas of charge. So acids and bases all have areas of charge, and they are all electrolytes. Covalent compounds like sugar or pure distilled water do not conduct electricity because they do not ionize or dissociate. Okay, acids are going to be all about the hydrogen ions. Every acid makes H plus ions. This is what you're looking for, sometimes also referred to as protons in this unit, or remember that I said H plus aqueous is the same as a hydronium ion, H3O plus 1. They're all electrolytes, so they'll all conduct electricity. They react with metals to release hydrogen gas. You remember from the redox unit, we have reference table H. If something is higher than hydrogen on reference table H, that means that that metal is more likely to be oxidized, and therefore that means that these hydrogen plus ions that you're going to find in every acid will be reduced. So H plus to H zeros means we're going to make pure hydrogen gas. Magnesium is a really common example, and this is the one that we've used in lab class. Zinc also very commonly used to produce hydrogen gas in our labs. There are acid-base indicators on reference table M. Really common ones that are used to tell whether you have an acid or a base will be phenolphthalein and litmus. The way this table works is that at any pH lower than the first number, it's going to be the first color. At any pH higher than the second number, it's going to be the second color. If it falls somewhere in the middle, you usually get something in the middle. For example, thymol blue. If I have a pH lower than 8, so say I have a pH of 6, thymol blue will be yellow. If I have a pH of, say, 11, thymol blue will be blue. If I have a pH of 8.5, it's going to be a green color. As we work with acids and bases and we neutralize them, you'll see this color change when we use indicators. And you kind of get the in-between color. Litmus is often coated on paper, and we use it to really quick test whether we have an acid or a base. Acid will be red with litmus. bases are blue. Phenolphthalein we've used before in lab. If you have an acid, it's colorless. If it's a base, it's pink. We will practice using the chart in class. Make sure you understand lower than the first pH, first color, higher than the second pH, the second color. Acids taste sour. Think lemons, vinegar, any of those type of acidic things. They have a sour taste to them. Tasting acids is not a safe way of deciding whether you have an acid or a base. Do not taste any acids or bases. There are two definitions of acids and bases that you are responsible for knowing. One is the Arrhenius definition, and that's dealing with ions. So it's going to say for acids that acids make hydrogen ions in solution, so H pluses. So all of the acids that you look at generally start with hydrogen for their positive ion. When we make them aqueous, they dissociate, and we end up with the H pluses. The other definition that the state calls the alternate definition of acids and bases, its real name is the Bronsted-Lowry definition, so we're just going to call it the Bronsted-Lowry definition, says that acids are proton donors. So if we look at what happens here, this is where the hydronium ion comes in. Instead of saying it's H plus aqueous, we're going to look at where that hydrogen goes. Where does the proton go? So remember, H plus is the same thing as a proton. So if I have HCl and water, I end up with H3O. So this hydrogen went to this water, and the chlorine is left over here. So this HCl donates the H plus to the water. That makes him a proton donor, and it makes him an acid. Okay, alternately, it means that our water over here acts like a base, but we'll get to that in another lecture. There's a chart of the common acids. 99% of the time, if they're using an acid on your final, it's one of the ones that you will find on reference table K. So formulas and names are listed for you. There's no excuse to get them wrong. Watch out for things like carbonic acid, because carbon dioxide aqueous is the same thing as carbonic acid. This is why pop is bad for you, rots your teeth, weakens your bones. Don't drink it. And then ethanoic acid goes by two names. Ethanoic acid is the organic version, and that's going to be CH3COOH. Acetic acid is the way an inorganic chemist would look at it, as in hydrogen acetate. They are the exact same thing. Same numbers of carbons, same numbers of hydrogen, same number of oxygens. Just in the ethanoic acid, this H at the end of your COOH, that's called the carboxyl group. It looks like this. This hydrogen down here is the one that breaks off. I'm sure you all remember that from organic chem in biology last year. In the inorganic chemist way, it's easier to see where the hydrogen is. Bases also are electrolytes. That same reference table with the indicator works for bases as well as acids. Really common ones are the phenolphthalein with the really pretty pink, and litmus is blue, blue for a base. Starts with a B, you guys remember. Bases taste bitter. If you've ever bitten into a chunk of baking soda, or I'm sure none of you have had your mouth washed out with soap, but if you've accidentally gotten soap in your mouth, they taste pretty bitter. Soaps are bases, so bases taste bitter. Again, don't taste any clear liquids to see if they're an acid or a base. That is not a safe way of deciding. So in our Arrhenius definition, bases make hydroxide ions, or the OH minuses. So sodium hydroxide, really easy to spot. Calcium hydroxide, potassium hydroxide, these are our most common bases, easy to see. They did, however, and this is where the Bronsted-Lowry definition comes from, there were things that acted like bases that didn't have a hydroxide in them. So ammonia, if we look at our table of bases, table L, right at the bottom, NH3 is considered a base. It did all the same thing that other bases did. It was slippery, it tastes bitter, it neutralizes acids. So they had to come up with an alternate theory, and the alternate Bronsted-Lowry theory is that bases are proton acceptors. So if we look at the NH3, it's turning into NH4. The difference is that it gained an H+. So NH3 to NH4+, gained an H+, so the NH3 is a proton acceptor, and a proton acceptor is a base. Where did it get the proton from? It got the proton from the water, who turns into an OH-. This base, or this water, donated the proton, so the water is an acid like we learned just up top. Notice in our products we still end up with an OH-. The last thing we need to talk about is amphiprotic or amphoteric substances. Just like amphibians that had two forms, this amphi prefix means that these substances have two forms. They're things that can be both an acid or a base if we use the Bronsted-Lowry definition. There are a number of substances that can do this, but the only one you really need to worry about is water. So if we look at this first water, for example, and it's H2O, it turns into H3O. How do you go from H2 to H3? You have to add an H+. That means that this H2O is accepting a proton, and proton acceptors are bases. This other water, then, would have to be where the proton came from, and he's going to lose a hydrogen. So to go from H2O to OH, two hydrogens to one hydrogen, you lose an H+. So he is donating a proton or losing a proton, and so this water is acting as an acid. In the reverse reaction, the opposite would be true. The H3 is going to turn into H2 by donating a proton, so he's the acid, and the OH is going to turn into H2O by accepting a proton, so he's the base. So amphoteric can be both an acid or a base. This is going to be extremely important when we talk about pH later in the unit. So make sure you know this for when we talk about the pH scale. And that wraps up Lecture A.